All eyes are on the Arctic. Many states are engaged. Most of them are also democratic. There is a lot to be content about. But foreign policy is like Arctic weather. It can be beautiful. It can be dangerous. At least unpredictable. When we head to the mountains, we must be prepared for all weather conditions. The mountain codes are drafted to ensure a safe and memorable trip. These mountain codes are also relevant for Arctic development. Here are the Arctic Frontier's 7 mountain codes for a sustainable future beyond borders. 1. Development in the Arctic must happen on our terms. 2. Trust science. 3. In quest for solutions, the map is our theory, the terrain, traditional knowledge. 4. Choose safe paths. Invest in local communities, technology, and education. 5. Our survival kit is robust infrastructure and collaboration beyond borders. 6. The cookie cutter model doesn't work in the Arctic. There's no shame in turning back. 7. Always know where you are. Follow these mountain codes and we can build a sustainable future, no matter the political weather. Enjoy the hike. Welcome to Arctic Frontiers 2025 Beyond Borders.
Velkommen til Tromsø og Arctic Frontiers, våre båten. Vi møtes her for å diskutere muligheter og dilemmaer. Klima og miljø, handel og utdanning, sikkerhet og beredskap er alle områder som er grenseoverskridende. Her i den arktiske hovedstaden så møtes vi for å løse de store utfordringene. Skaff deg nettverk, bruk tida og finn deg en ny venn. Vi er deres venner og ønsker dere velkommen hit.
Arctic Frontiers has become the place where we gather the most important voices from the Arctic. In 2025, we meet again in Tromsø under the title Beyond Borders. And yes, that might sound a bit strange in a time when the world seems to be building more walls than bridges. But that is precisely why this meeting is so crucial. With increasing geopolitical tensions and climate challenges, we really need to talk to each other. We need to share knowledge, listen to one another, and create hope for a better future. Arctic Frontiers was started 18 years ago by some truly visionary researchers and business leaders. They understood that we must bring politicians, researchers, and the business community to the same table. Because good decisions require insight, not just opinions. In the Arctic, we have always known that we depend on each other. Our extreme conditions have taught us that cooperation isn't a choice, but a necessity. We share knowledge, we build friendship across all borders. I often think of John Lennon's song Imagine, which is about exactly this. Imagining a world where we look beyond what divides us. Let us use Arctic Frontiers 2025 to do more than just dream. Let's take action. I look forward to meeting you. Welcome.
Kjære alle sammen, velkommen til Tromsø, den arktiske hovedstaden. Mens verden rundt oss er i endring, tar vi tak i de store spørsmålene fra Tromsø. Hvordan skal vi leve det gode og trygge liv mens krig, ressursknapphet, klimakrise og naturutfordringer for øvrig er rundt oss? Det svaret må vi finne sammen. Det som virker i Arktis, det virker alle andre plasser i verden. Lykke til med konferansen, og lykke til med alt arbeidet. Takk for meg.
Boris Poetem, On behalf of the Sami Parliament, it is both my pleasure and honor to welcome you all to Sápmi, the homeland of the Sami people. I would, of course, also like to welcome you to the fantastic Arctic Frontiers 2025. Unfortunately, I am unable to attend the Arctic Frontiers this year. As many of you know, the Sami people live across borders in Finland, Norway, Russia, and Sweden. Therefore, this year's theme, Beyond Borders, resonates with us. We aspire to be Sami with as few obstacles as possible from national borders. Tromsø, or Romsa as it is called in the Sami language, is a Sami city and home to many Samis. However, in the past, Norwegianization and border closures have significantly impacted the Sami community in Tromsø, restricting their movement and affecting their cultural and economic practices. Therefore, I highly recommend a visit to the Tromsø Museum during your stay. The museum features exhibitions that showcase both the traditional Sami way of life and the modern experiences of being Sami today. With these words, I wish you stimulating discussions and a successful, enriching conference. Enjoy your time in Tromsø. Kiitos.
Over the past 30 years, the Arctic Monitoring and Assessment Program, AMAP, has been at the forefront of raising awareness about Arctic challenges and bringing them to the attention of the global community. The Arctic Climate Change Update 2024 report highlights these key indicators: rising temperatures, changing precipitation patterns, shrinking sea ice, Arctic greening, reduced snow cover, and increased burnt areas. Extreme events in the Arctic are changing in frequency and intensity. The rapidly changing cryosphere is affecting ecosystems throughout the Arctic, changing the productivity, seasonality, distribution, and interactions of species in terrestrial, coastal, and marine ecosystems. Flows of fresh water funneled into the Arctic means the region has a crucial role in regulating the global climate and ocean currents. The acidification of the Arctic Ocean is increasingly evident, with continued observations showing a rapidly changing marine carbonate system. Climate change is driving rapid changes in the Arctic that affect people, especially indigenous peoples, living in the Arctic and beyond. Changes in the Arctic have global consequences. This report also covers Arctic and mid-latitude weather connectivity. This report reiterates the need for enhanced action to meet the long-term temperature goal and effective implementation of the Paris Agreement.
Thawing permafrost, disappearing glaciers, disappearing sea ice, people, culture, nature, communities under pressure. This is not a scene from a science fiction movie. This is reality, such as we just saw on this movie. And it is reality of people and communities in the Arctic. My name is Maria Varteresian. I am a State Secretary and Deputy Foreign Minister of Norway, and it is my great pleasure to welcome you all to this launch of a report by AMAP, Climate Update. An important delivery under the Norwegian chairship of the Arctic Council, Chairship, which you know has been quite difficult due to geopolitics, not due to the Arctic Council in itself. But regardless, the fact that this report is released, it is presented, it is timely, it is important, and it shows that the working groups are delivering and that the Arctic Council is very much alive. 427. Now, I'm sure that to many of you in this room, this number has a meaning. But to those of you who don't know what it is, I can say that it is the number of parts per million, symbolizing the amount of CO2 concentration in the atmosphere this year. And it is expected to rise. Now, 353. That was the amount of carbon dioxide in the atmosphere the year I was born, which was 1989. So what we can see with facts, we know for sure that as the global relations, they cool down, because they have, the temperature of the planet, well, it continues to increase. And that in a time where cooperation to cut emissions has been more important than ever, at the time where we need the will among politicians to cooperate more than ever, it is also a time where it is more challenging and difficult than ever. And that is why we need the Arctic Council to continue to live and to continue to deliver. Now, one of the main findings in this report, which is released just a little more than 20 years after the first significant landmark, I would say, report by AMAP, really pointing to the fact that climate change, it's not something in a distant future, it's happening right here, right now, and it affects our lives, our communities, the whole planet's ecosystems, well, 3 times faster than the global average. And it is man-made. It is made by the fact that modern economies have developed on the basis of taking a little bit too much from the nature, living a little bit too much of what we don't want in terms of CO2 emissions, in terms of pollution. But regardless, it is affecting everything around us, and we must cut, adapt, prepare. Now, it sounds so easy, but why haven't we been able to do more? Well, the short and the long answer, it's politics. And I'm a politician, so don't get me started on that. But regardless, we need solid knowledge base to guide us. We need a knowledge-based approach to guiding the policies. My boss, Mr. Espen Barth Eide, the foreign minister, often says, "Fakta må ha makta." That means that facts must have power, facts must lead the way, but in order for facts and research and knowledge to get power, it is important that it is presented in an understandable way so that politicians, such as myself, I'm not a researcher, can understand. But it's one thing to understand. The second thing, and that is the most important one, is to use what we see and what we understand to guide the decisions and politics and choices that are made by politicians. Because without facts, we are blind. So, dear all, it is my great pleasure to once again welcome you to this launch of the key findings of the AMAP Climate Update Report. And thank you so much for being here, and thank you so much for the attention, and thank you so much for the important work that you all are doing. Thank you.
Thank you, State Secretary, for those inspiring words. We're honored to have you opening our side event today. Good morning, everyone, all of you in the room, and also to the online participants here. On behalf of Arctic Monitoring and Assessment Program AMAP, I would like to welcome you here today to gather our focus on the changing Arctic climate and the challenges it presents to our planet. My name is Maria Kvalvåg, and I'm a Deputy Secretary at the AMAP, and I will guide you through the program today. So, today we will have, for the first time, a presentation about the detailed key findings from our latest climate update report. And we have the privilege of hearing from some of the most recognized voices in Arctic climate science and research. Before we begin, let me briefly guide you to the program today. For the first hour or so, we will have a series of presentations from authors of the report, both people in the room, but also 2 remote speakers. And then we will transition into a panel discussion, joined by 3 distinguished guests, which we look forward to hear about, and to broaden our perspective and relate the findings of the report to the work of the IPCC, WMO, and Polar Research. There will be opportunity to ask questions to the speakers and to the panelists. And if you're joining us remotely, you may send your questions to amap@amap.no, and we will have it read it up loud. But first, let's start. I would like to give the floor to my colleague, Dr. Rolf Rødven, the Executive Secretary of the Arctic Monitoring and Assessment Program, who will speak to us about AMAP and the background for the report. Welcome.
Thank you so much, Maria. Dear State Secretary, dear colleagues and friends, today is a big day for the Arctic Monitoring Assessment Program. This is our first launch since 2021. It's a significant achievement in resuming the work of the Arctic Council, and it's very important also for bringing the Arctic climate to the global agenda. And on such a day, it's the right occasion to put on your finest clothes. However, there's another reason for me to put on these clothes right today. And that is due to the fact that the 16th of January, Dr. Robert Correll, or Bob Correll among friends, passed away. He was the chair of the Arctic Climate Impact Assessment, which has already been mentioned, which was a milestone on putting the Arctic on the global agenda in regards to climate change. He was also a contributor to this report. And also, I would like to say, which is important for the Arctic, or for people living in the Arctic, Bob Correll was one of the most important spokesmen for bringing together indigenous knowledge and science for improving our understanding of climate change, how we adapt, and how we mitigate. And in respect of Bob's memory, I put a magak today to show where, just to symbolize those 2 things to put together. AMAP has since 1991 been assessing and monitoring levels and trends of contaminants as well as climate change in the Arctic, how they affect the ecosystems as well as the livelihoods, and how they interact also on their effects on also human health. So why is the Arctic important? Well, for me, the answer is obvious, because it's my home. But it is important on a global scale. It is the canary bird of the globe. When it comes to contaminants, the Arctic is the most sensitive indicator of contaminants, which have led to the Minamata Convention and the Stockholm Convention regulating some of those. When it comes to climate change, the Arctic is, literally speaking, the hotspot of the globe. Climate change is happening 3 times as fast in the Arctic as elsewhere. And it does have some of the fastest rates of ocean acidification. And what happens in the Arctic do not really stay in the Arctic. It has feedbacks globally, primary feedbacks like sea level rise from glacial melt, from greenhouse gas emissions, from permafrost thaw and wildfires, but also secondary impacts like true societal impacts, like effects on fisheries and other ecosystem services. To address the state of the Arctic, AMAP do run a throughout assessment process. AMAP assessment work relies on an expert pool of more than 800 experts worldwide. However, it is in the interaction between heads of delegates and experts the added value origins, where through dialogue, specific policy-relevant scientific questions are developed, facilitating science-based policy and recommendations as an end product. Okay, there we go. This year marks 20 years since the launch of the Arctic Climate Impact Assessment Science Report, which was excellently led by Dr. Bob Correll. This was a milestone in putting the Arctic on the map with regards to global climate change. However, it was regarded a bit controversial by some experts, because some of our experts some of our estimates were more radical than others, like IPCC ones. However, looking back in retrospect, we do see that if the report was controversial, it was due to it being more conservative than what it shows today. The change is happening faster than we expected. And that is due to Arctic amplification. And that is also the reason why AMAP in 2019 decided to do biannual updates to keep up with the pace of the change going on. These updates focus on indicators as well as selected topics to bring forward for information. They do complement our other more in-depth assessments, and also they're meant to complement other assessments, like for instance the longer cycles of the IPCC reports. In the current report, we do focus on 7 main areas. It is the climate indicators, climate extremes, wildfires, the cryosphere, hydrology, ocean acidification, as well as weather connectivity, where Bob contributed. And by that, it's also now for me to welcome the chapter authors to the stage and to thank you so much for your attention.
Honoring one of AMAP's highly appreciated experts. So let's move over to the first presentation about the key findings from the update report. Our next speaker is Dr. Rasmus Benestad, who is a senior climate scientist at Norwegian Meteorological Institute. Rasmus has also a central role in AMAP, leading the climate expert group. And he will talk to us about chapter 2 and 3 in the report. So Rasmus, the floor is yours.
Thank you, Maria, and good morning to everybody. So I will talk about 2 chapters in the AMAP Arctic Climate Change Update 2024. I'll talk about key indicators and Arctic extremes. The key indicators give us a very good summary of both the trends and the status of various perspectives of both the environment but also climate in the Arctic. And in this report, the key indicators are presented as graphs which show how things have changed over time. The first key set of indicators that we present are temperature-based indicators. One for the Arctic, but also, as you said, the Arctic has changed twice as fast as the global mean. So the orange graph here shows the Arctic mean temperature, and the vertical axis here shows the temperature, and the horizontal, the time. And the dark blue graph shows the global mean temperature. So you can see that it changed. It has warmed faster in the Arctic, and you can see on the right, these graphs are summarized in text. So it's about 3 times as fast. Also shown here on this graph is the Greenland ice sheet's temperature at 10 meters depth as well. And you can see that that has changed quite in a similar way to the temperature. Another set of indicators that we present here are precipitation indicators. Now, when it comes to precipitation, the data is not quite as complete as the temperature. And there are different sources of data as well. So we have 2 curves showing the precipitation. And they differ. The statistics differ a little bit here. So the first one here is the Global Precipitation Climatology Project, the GPCP, which is a light blue curve here. And that is a blend between satellite data over land and ocean, but also rain gauge data over land, because the rain gauges are only over land. And the other one, the dark blue, is what we call the ERA 5 reanalysis. So these are archived weather forecasts, but this is a blend between observations and model simulations. And ideally, they should show the same thing, but in this graph, the axis on the left is for the GPCP, and the axis on the right is for ERA 5. And you can see that they have different values, so they have different amounts of rainfall estimated here. But they both show an increasing trend. We see more rain in the Arctic. And we can also see this if you look at the river discharge in the Arctic region. And we have a set of indicators for the river discharge as well. And here are two, so this is a different type of graph. The dark blue columns show the river discharge in North American Arctic, and on top of that, the light blue, I hope you can see it, is for the Eurasian part. And then at the top of these bars is a total of the two, and then there's a trend line at the top here. When it comes to hydrology, Johanna Moore will talk more about it later, so I will move on to other types of indicators. One thing that I also want to mention is that river discharge is not just rainfall, but also melting snow, melting ice, and thawing permafrost. And that brings us to these cryospheric indicators. Let's see. Yeah, there you are. The cryosphere is the frozen part of the planet, or the frozen part of the Earth. These two curves here show changing snow cover extent. That's the light green, but it's only snow cover over land, so it doesn't include the sea ice. And the darker curve here shows the Arctic sea ice extents in September, when it's a minimum. And you can see from both of these, the story here is that the ice is melting and we get less snow, and that is due to higher temperature, but also more rain than snow falling. So then there's less accumulation of snow. But also the wind patterns affect this, especially for year-to-year variations as well. We can see the melting even more clearly if we look at the land ice in the Arctic. And here on this graph shows the ice mass, land ice mass in the Arctic Canada, on Greenland, and also the purple one is the sum of all of this, and also Alaska. And we see that the melting is actually accelerating over time. It's going faster, at least for a while, until there's no more ice left, and then it will stop, of course. Sebastian Gerland will talk more about the cryosphere later. But we can also, this report also presents some other types of indicators, oceanic indicators. Here is one showing increasing Arctic acidification. So this shows that the Arctic seas are becoming more acidic due to the uptake of CO2. It's actually in a way good that they do that, because otherwise there would be more CO2 in the atmosphere, but it's not good for marine life. And this curve shows the hydrogen ion concentration. So that's nanomoles, sorry, I'm a physicist, not a chemist. Nanomoles per kilo water, and you can see that there's increasing ions, and it gets more acidic over time. I think Agnes Fransson, will talk more about these ocean indicators later on today. So I will also present some other types of indicators of this report, which are more on the environment, biological indicators. So there's this normalized difference vegetation index, as NDVI. That is measured from satellites that shows the state of the vegetation, but also both the density and also the amount of vegetation. And here is two graphs. One, the dark blue shows the maximum MDVI in the year, and the green is the time integrated NDVI each year. And these both show an increasing trend, which indicate that the tundra is becoming greener. There's more vegetation growing on the tundra. So that is also an indication of changing climates and environment. And also, in addition to this biological indicators, we also have some indicators more relevant to society and also nature. So these are the hazard indicators. Here are graphs showing the area burnt down by wildfires each year in the Arctic. And you can see there are various, some start later and some earlier. This doesn't show a clear trend, a systematic trend. But Mark Parrington will talk more about this later in this series of talks. When it comes to these wildfires, they are a consequence of extremes. And that brings me to the next chapter, Arctic extremes. And I'll present like an overview of various types of extremes here. And in this case, extremes can mean one of two things. Either it can be some event that has been that is rare compared to what has been in the past. So, or it could also be defined in terms of its intensity or its consequences as well. So this graph here shows the number of events recorded by the Local Environment Observer, or LEO, database for a period 2017 to 2022, so it's a 5 years period. And what you see here is that most of the events or extreme events have involved extreme temperatures. And the second one is the sea ice, and then we see like the wildfires actually down on a list there, but still they all count as extremes. And some examples of recent extremes include loss of sea ice in the Barents Sea. So, and that is an extreme sort of event on a longer term. It's not like a sort of very sudden extreme. So when I'm working at the Norwegian Meteorological Institute, we tend to think of extremes more as weather, but these are different types of extremes. But also the heat wave extremes in Siberia, which is more like what I'm used to, and a loss of snow on Greenland. So climate change, the Arctic amplification, but also the natural variability, like the day-to-day variations in the weather, provide new extremes. And the global warming leads to temperature rise, but also thawing of permafrost. That leads to new types of extremes in terms of like sea loss, open water, but also new biological or environmental extremes as well. So that is, in a nutshell, these indicators and also the extremes that is presented in this report. So by that, I actually used less than my time, but I think that is okay. I would like to thank you for your attention, and
we have time for, if you come on stage, Rasmus. There is time for a question, because this chapter 2 in the report is kind of summarizing the whole report in its indicators. So you have touched upon many topics that we will hear more about later. But we have time for one question, if there's anyone here. And to our listeners, please send your email to amap@amap.no if you want to. Heidi will check that. We can also come back to that later. Thank you so much, Rasmus. Our next presentation is from a remote speaker. Dr. Johanna Mård is a researcher in water and climate at Uppsala University. She is also co-leading the AMAP Climate Expert Group together with Rasmus, and she will now present the key findings from the chapter 6 on terrestrial hydrology that she was leading. So I hope the technicians is with us, and the floor is yours, Johanna.
Can you hear me?
Yes, we can. Great.
Okay, and you can see the full screen.
Perfect.
Everything is working.
Yes.
Okay, thank you very much, everyone. So good morning, everyone. So I will now present you the key findings from the terrestrial hydrology chapter. And this chapter is intended as an update on the Arctic terrestrial hydrology since the Arctic freshwater synthesis that came out in 2015, as well as the SWEPA report that came out in 2017. And I would also like to first acknowledge all the co-authors that was involved in finalizing this chapter. So what this chapter is covering is many different components of the terrestrial hydrological system, including precipitation and snow cover, permafrost hydrology, river discharge, surface water, river ice, lake ice, as well as freshwater contribution from land ice, and finally a small summary of the impacts of hydrological change on ecosystem and Arctic livelihoods. So here I'm going to present then the key findings from these different sections. So as we already have heard, when it comes to precipitation and snow cover, so precipitation has increased over recent decades, especially in the cold seasons. And what we see is that these changes are associated with an increase in rainfall in all seasons, which is here illustrated on the left-hand graph for northern Canada and Eurasia, as well as a decrease in the snowfall water equivalent in summer, with spatially varying trends in the winter, which is shown here in the right graph. Looking at the snow mass, which has decreased across northern North America, but in Eurasia, the trend has been negligible, and snow depth has also increased in parts of Eurasia as well. And looking then a little bit on the extremes, so precipitation events that are presently being regarded as extremes are something that is expected to become also more frequent. And these changes also impact the river regimes in the Arctic, among other things. Moving over to permafrost, well, permafrost thaw is likely to drive changes in the water balance in Arctic areas. But the relevant subsurface processes are difficult to observe directly at catchment scale. But observed changes in stream flow dynamics and water chemistry indicate that thaw is influencing hydrological connectivity in Arctic catchments by creating deeper and longer waterfall pathways through catchments across the Arctic. When it comes to river discharge, we see that annual river discharge to the Arctic Ocean continues to increase from both continents, and this is continued to provide compelling evidence of intensification of the Arctic water cycle. And this graph shows the discharge trend from the 8 largest rivers in the Arctic, which makes up about 70% of the whole Pan-Arctic drainage basin. Apart from these sort of long-term trends, we also see a significant increase in the base stream flow during the cold season across most regions of the Pan-Arctic drainage basin. While looking at the maximum river discharge, this has not changed significantly when it comes to the magnitude. But what we do see, however, is that the timing of snowmelt freshet has become earlier almost everywhere across the Pan-Arctic. Continuing with surface water, so what we can see is that lake area is declining across the discontinuous permafrost zone. So this is what is illustrated in the left-hand bar chart. While in the continuous permafrost zone, the number of sites with decreasing lake area is similar to the number with increasing lake area, which is illustrated in the left-hand bar chart. So the stronger lake area declines in the discontinuous permafrost zone is also consistent with permafrost thaw being further advanced here than in the continuous permafrost zone. For river ice, ice cover duration on rivers has declined significantly in cold regions over the past several decades due to the later freeze-up as well as earlier breakup. And this is exemplified here on the slide, which shows locations of Eurasian river gauges and their changing river ice phenology during the period 1955 to 2023, which is showing a duration of ice events which has decreased significantly. When it comes to maximum river ice thickness, this has also decreased on most Pan-Arctic rivers over the last 50 to 60 years, but the greatest decrease observed before 2000. And this observed decline in river ice is likely also to continue in the future due to the projected increase in air temperature. When it comes to lake ice, this is also rapidly losing across the northern hemisphere with later ice on date and earlier ice off date. And in some years, some lakes not freezing at all. And this map is showing current and future northern hemisphere lakes that could experience intermittent winter ice cover with climate warming. So the orange regions are showing the current conditions, while we also see projections between 2 and 8 degrees warming, illustrating purple, yellow, blue, and red. And we also have other lakes that are shown in black. And finally, what is being covered in this chapter is also the freshwater contribution from land ice. And freshwater contribution is roughly equivalent to that from the North American rivers, while Eurasian river discharge is roughly 3 times higher. However, the increase in Arctic river discharge was about 1.6 times smaller than the increase in freshwater flux from the Arctic land ice. And most of the increased land ice freshwater discharge originated from Greenland and Arctic Canada, which is also illustrated in this graph that you see here. And further increase in the freshwater flux from land ice reduction is also likely to continue with projected future increase in Arctic warming. So finally, what does this mean then? All these changes that we see in the terrestrial hydrological system. Well, these changes have important impacts on ecosystem and Arctic livelihoods. For example, we see that decline in snow cover, permafrost, lake areas, and lake ice have implications for ecosystem, as well as hunting, fishing, reindeer herding, transportation, and drinking water availability. But these changes also include feedbacks, as we have been told earlier, to the climate and ocean circulation through increased freshwater fluxes to the Arctic Ocean, as well as the changes in lake areas and ice cover. And we have just covered a few of these impacts that can be on the ecosystems and Arctic livelihoods, but more of these implications will also be covered in the AMAP CAF project, as well as AMAP's upcoming report on societal implications of climate change in the Arctic. So thank you very much for listening to this terrestrial hydrology chapter.
Thank you, Johanna. You can still have the video of Johanna in case there are questions for her on terrestrial hydrology. Anyone? Yeah. Thank you.
Thank you. If I may take the floor, I have a quick question for you, Johanna. You've talked about the increasing contribution of melting land ice to the amount of fresh water being discharged into the Arctic Ocean. What is the implication of that on ocean acidification?
You're muted, so do you have your...
Sorry, that is a very good question. I think I will forward that to my colleague that will present the Arctic acidification later on today.
Yeah, that's okay. Thank you so much. And thank you, Johanna, for joining us today. And then we will go over to our next speaker, which is in the room. And I would like to introduce you to Dr. Sebastian Gerlan. He is a senior research scientist for sea ice and climate and a section leader for the section Sea Ice at the Norwegian Polar Institute Research Department. And he will introduce us to the key findings from the cryosphere chapter. Sebastian, the floor is yours.
Can you hear me? It works? Yes. Perfect. State Secretary, everybody, good morning. I was invited to speak about the cryosphere. Thank you for that. And everybody who came here this morning had contact with the cryosphere because it was quite icy around. And we heard already from Rasmus Benestad the definition of the cryosphere. I just have to see how to get this further. See the green big. Yeah, thank you. So the cryosphere, as we heard, describes the parts of the Earth's surface with frozen water present, permafrost, snow, land ice, and sea ice. And I will tell you a little bit about these 4 different parts of the cryosphere. This report's chapter about the cryosphere was led by Nguyen Wang, and contributing authors are Sharon Smith, Jason Box, you saw him in the video in the beginning, myself, Kjetil Isaksen, Walt Meyer, Lawrence Mudryk, Susan Nathalie, Vladimir Romanovsky, Michael Siegmund, and Quy Shu. Was one too fast? Let's see. Here we are. So permafrost, snow, land ice, and sea ice. These different types of or parts of the cryosphere, they include again number of subtypes. Some we heard already about. Of course, you have in land ice glaciers, ice sheets, river ice also. And for snow, there's of course many types of snow on land, snow on sea ice, and then sea ice. In sea ice, we have many types there as well. But I will guide you a little bit through these 4 types. So starting with the permafrost, it's one of the examples of the findings from the report is here the increasing ground temperature over recent decades for different regions, and do not see all the details there. It's a time series from the 1970s to recent. So it goes over several decades, and it shows the permafrost temperature for anomaly for different regions. So the red one is interior Alaska and the Mackenzie Valley, and the blue one is Beaufort-Chukchi Seas, northern Alaska, and purple is Baffin, Davis Strait, eastern and high Arctic Canada, and the green is the Barents region. So what you in general can see is that they are all increasing several degrees, and but there are regional differences. That of course makes it also interesting and important to make observations in the different regions. So moving over to snow. In snow, we heard already, we see a reduction in snow. That was already said in general. In this cryosphere chapter, we could look a little bit more into the details of how the snow is changing. So again, different regions for the snow changes were looked at. So the bit maybe on the first view confusing to graphs. They have data for Eurasia, North America, and the Northern Hemisphere in the top graph, and that's the snow cover extent May to June in million square kilometers. So of course, satellites give us information on snow cover, and extent is then basically at the area where you have snow, and we can see that they are decreasing with the biggest changes for the uppermost curve, the Eurasia curve. And the lower graph shows you snow mass, because the snow cover is not telling so much about how thick the snow is, how much snow, how much snow water equivalent is there. So the snow mass is shown here for Eurasia in blue and for North America in red. And we can see here that also there we have negative trends, again for North America, a bit less strong than for Eurasia. So we can see here also, if you look at just a few years, we can see the mean values jumping a little bit up and down. So this shows also that it's really necessary to take long-term time series of these data in order to see really climate changes. From snow, I'm moving over to land ice and sea level changes. And also here we heard a bit already, we saw the curve about the land ice change, how ice is decreasing in volume. And of course, the consequence is then that sea level is increasing. And these are the contributions from losses of Arctic and also Antarctic land ice since the 1970s in this curve. And again, you can see curves that are not only linear increasing, they're really accelerating, and at least over this longer time span from the 70s to now. And the uppermost curve in this, that's all Arctic, including Alaska. And then below is curves for different parts of the Arctic, and also there's one curve there for the Antarctic, and that's a curve that's in the middle of that set of curves. It's a little bit shorter at the end. The data are not that long there on the plot, but you can see that as of now, the Arctic is really the big contributor there compared to the Antarctic, even so the Antarctic has a huge volume, which of course has also potential for contributions later even more. But even in the Arctic, we have smaller glaciers and ice masses, but that all in combination, and in combination with the increased temperatures, results in that the Arctic is altogether the largest contributor here, and that's a sea level increase there of about 30 millimeter from the 70s to now. Then moving over to the subject I'm working in myself, that's sea ice, and here, of course, Arctic sea ice. And we heard also already that Arctic sea ice is decreasing, and that we can see also in these two curves that show Arctic sea ice extent for the winter, the maximum extent in the upper curve, and the summer, the minimum extent in the Arctic in the lower curve. What's probably a bit too small on this display there is that we also plotted the gradients for decades in these curves. The curves start in 1979. That's the time when the passive microwave satellites started to be operative, and we get continuous data of CS extent from those satellites. And we can see that there are really differences, especially for the summer, in how the decadal changes developed. And we can see around 2007 a very big change there also, where it's really going down. And I guess some of you remember 2012 is this record minimum where we can see the lowest peak in the lower curve. But in the recent decade, we can see it has been always much lower than it used to be in the 80s and 90s regarding CS extent. However, CS extent is also then regionally different. And that we can see in the even smaller maps to the right there, but that is then showing ice extent for different months of the year, for 4 selected months: March, June, September, and December. And December is the map in the lower right, and we can see here Hudson Bay and Barents Sea as especially appearing with dark blue colors, showing the largest changes. So that's also, of course, important, looking here again at regional changes, not only at the complete Arctic changes, in order to understand the system and what is changing. What we also, of course, as sea ice scientists look at is ice thickness changes and ice type changes. The ice has become a lot younger on average, and it's moving faster. And also the ice has become, over that whole period, thinner. Moving to the key findings, just to summarize the key findings from the cryosphere chapter. All in all, the conclusion is that since 1980, the Arctic cryosphere has diminished, both on land and over the ocean. The melt season has lengthened, while the freeze season has shortened. And then regarding permafrost, the permafrost has warmed and thawed over the past 4 decades, which has led to landscape change, especially where permafrost is ice-rich. Permafrost degradation will continue in response to increasing air temperature, but there's less certainty regarding the magnitude and timing of permafrost loss. When it comes to snow on land, we just saw in the graph, snow cover extent on land has declined substantially in spring and fall based on a combination of multiple snow products consistent with earlier assessments. Seasonal maximum snow water equivalent is projected to decrease across much of the Arctic, but regional increases are expected in eastern Siberia and the Canadian Arctic archipelago. That's one of the findings that I had not time to go into much detail, but later, once the report is out, you can also read details about that. Projected spring snow cover extent and snow mass show nearly linear response to the increase of global mean near surface temperature regardless of emission scenarios used in climate model CMIP6 simulations. And to the key findings about land and sea ice, the largest sea level rise contributions are glacier melt from Greenland, Alaska, and Arctic Canada, resulting from amplified Arctic warming and increasing moist atmospheric rivers reaching Greenland. And for sea ice over the 43-year record from 1980 to 2023, the decline of sea ice extent is greater in September, annual minimum, than in March, annual maximum. Decadal variability is also more pronounced in September than in March. The largest decline occurred in 1993 to 2006. And the evolution of sea ice shows large regional variability based on satellite data from 2011 to 2022. This is satellite data from altimetry satellites that measure the distance from the satellite to the surface and derive ice thickness from that. A sea ice-free Arctic summer is projected by mid-century based on coupled climate models under the low or moderate greenhouse gas emission scenarios. So that's summer, and mid-century is 2050 then, yeah, that's what I had. Thank you very much.
Thank you so much, Sebastian. We have time for one question, if there anyone in the room wanting to ask a question about the cryosphere. We have people running with microphones. Yeah, thank you.
Hi.
Go ahead. Please say who you are and where you're from.
Hi, I'm a researcher on glaciers from University of Oslo, and I'm wondering about the fact that these changes can be irreversible, and what would be the time scale to get back to, let's say, a pre-climate change normal state. Thank you.
Yeah, that's a very good question. The reversibility, and then one asks, of course, also, and you put that into your question, the time scales when we talk about reversibility. What we are looking at for this is a lot of paleo data when we see how did changes actually work in the past, how long took it time to go from a cold period to a warm period, and we combine that then with the knowledge about the processes. How is a glacier actually growing? How is a glacier decreasing? And then you come to this question about tipping points and so on. So it's very hard to answer this very specific. It's each cryosphere component can be different. Of course, if we have, we need to ask ourselves, what conditions do we need to create cryospheric components? If we need one snowfall here, we need the moisture, we need the temperatures that fit to that. If we want to produce sea ice in the ocean, we need cold enough water, we need cold enough air. It doesn't work if only one of the parts is like this. So and then it's a question how are the environmental conditions affecting these growing processes, like for glacier, for sea ice. If it's moving very fast, it might disappear, but it might also give some space for new ice growth. So it's really a very good and timely question what science works with as well. Thank you.
Thank you, Sebastian. And then we will go over to the next speaker, who is also joining us remotely. This is the time for us to hear about wildfires. Dr. Mark Parrington is a senior scientist in the Copernicus Atmosphere Monitoring Service at the European Centre for Medium-Range Weather Forecasts. And he has been the lead author for the chapter on Arctic and high-latitude wildfires and will present the key finding for us. Thank you for being with us here today on Zoom, Mark. Please, the floor is yours.
Okay, thank you. Yeah, it's a pleasure to be here. Thank you to AMAP and to Maria and Heidi who've been on the organizational side. Can I just confirm you can hear me okay and you can see my screen? I'm trying to make it full screen, but I can't see.
We can hear you, but it's not in presentation mode.
It's, I lost my index. So it's the first time I'm trying with the PDF for a while and have to find the control.
Sure.
Just 1 second, let me unshare and see if that helps.
Yes.
But I really apologize for this. Yeah, I'm not very well prepared. So hopefully now it's
it's okay. Fine. Thank you. Perfect.
Okay, great. Thank you very much. Okay, so thanks again to AMAP for the opportunity to contribute this by leading this chapter for this report. This is the first time there's been a chapter specifically on Arctic wildfires. This wouldn't have been possible without my co-authors who are listed here, so Jessica McCarthy, Hugh Haldo, Morgan Crowley, Mike Flanagan, and Merritt Turetsky. And just really to cover the breadth of the information and the environmental interactions that revolve around wildfires, well, globally, but specifically in the Arctic. So I don't have a lot of time to do this a lot of justice, but I can present the key findings, two of the main sort of points, and of course, all the detailed information can be read in the report when it's released. So I'm going to start with the key findings. There's a lot of text. I've tried to highlight the key messages from each of them. But essentially, we've seen as a result of the changing climate, changes in the fire danger, fuel, but also fire occurrence, fire behavior. We'll see that there's a high degree of year-to-year variability. In fact, we saw this with the climate indicators, the graphic showing the burned area. But what we're seeing is the majority of these fires occurring in regions where there are human activities, but also where environmental change is providing the conditions for fires to burn at high levels and in a very persistent way. And there's a lot of work to do. There's a lot of emerging research over the last 4 or 5 years where we're understanding better and better how Arctic fires are behaving and also how the fuel and the environmental impacts are changing as a result of that. However, there's still a lot of work to be done, and so there's this constant need for improving capabilities for detecting fire ignitions and holdover fires in particular. I'll mention that briefly towards the end. And also a key point is the incorporation of indigenous knowledge. What I'm going to be showing is based largely on satellite observations. There's a lot more field work going on, but obviously with Gwich'in Council and other populations and organizations related to indigenous populations around the Arctic. There's a lot of knowledge there, which is essential to understanding how fires behave and how they change, and as well as the climate change. And then building on that, there's also various emerging research and monitoring technologies, such as new satellites, which will be launched in the coming years, which will help us to better monitor Arctic wildfires in more near real time. And this is all essential to understanding the vulnerability of the Arctic and high northern latitudes as well to wildfires. So I'm going to start with looking at some observations and looking at what we mean by the geospatial distribution of wildfires of the past couple of decades, and then start to look at to sort of boil it down a little bit to understand how it's been changing and what some of the impacts are. So here on the left are two images. These are satellite images that were taken in July 2020 over Boreal Asia, up in the Sakha Republic in Russia. And just to give us a sense of the scale of these fires and how they burn. So we can see in the top image the scale of about 15 kilometers. So these fire fronts are really existing over tens of kilometers. They can move very rapidly, and they produce vast amounts of smoke, as we can see for this image. Just to point out that the red colors you can see on the image are false color, which is based on a heat measurement of the fire. It's not actually images of the flames. And the bottom left is a bit more zoomed out. You can see the scale of about 50 kilometers and several fires that were burning during that period and in that year. And 2020 was one of the most extreme years for wildfires in the Arctic. The map on the right is showing the distribution of the highest energy fires for June, July, August, and coloured by decade. So the orange is the 2003 to 2009 period, and the darker colour is the 2020 to 2024 period. And so we can get a sense of where these fires have been burning over the past 3 decades, what it comes to now, and how that's changed decade by decade. So certainly we've seen a lot more fires in the Boreal Asia and the Siberian Arctic in the 2010s and 2020s, whereas for Alaska, we were maybe seeing more in the 2003 to 2009 period. If I move on to look at what this means year to year, on the left-hand side, I'm showing estimated carbon emissions from wildfires, which are based on satellite observations of fire rated to power, or the active fires. And this starts in 2003, because this is the Copernicus Atmosphere Monitoring Service, who I work for, their data set, and it's based on the two MODIS instruments on the NASA Terra and Aqua satellites, and the combined use of those starts essentially beginning of 2003. So the orange bars are showing the subarctic, which is fairly crudely defined as all latitudes between 60 degrees and 66.6 degrees north, and the red bars show the Arctic, which is all latitudes poleward of 66.6 degrees. So we can see there's a lot of interannual variability. 2019, 2020 were the really big years for Arctic wildfires specifically. And in the table at the bottom left, I'm estimating the annual mean totals, and then the sum over that period for the Arctic, subarctic, and then the combined Arctic plus subarctic regions. And the key takeaway here is, particularly if we look at the Arctic, in the right-hand column of this table, we see that already between 2020 and 2024, more carbon has been emitted from wildfires in the Arctic than in the previous decade, by about 20%, which was already almost half, 150% higher than what it had been in the decade prior to that. So we're certainly seeing a lot of interannual variability, but decade by decade, an increase in fire activity and fire emissions, as shown here. On the right-hand side, it's a very complicated picture, but just to take away what's highlighted by the red boxes, this is a study that was using satellite observations published last year. And the key finding of this paper was that the Northeast Arctic had experienced the highest growth in the satellite measured intensity over the past 2 decades since 2003. And the graphic on the right-hand side shows that this has been a big increase in boreal forests and taiga, so in the Arctic, but also the subarctic region. One of the main impacts for this, as we saw in the satellite imagery, a lot of smoke produced by these fires, they have severe direct air quality impacts which affect human health, but also the larger environment. What I'm showing here is just 2 studies that were published last year. On the left, very quickly, I'm highlighting that in the 2010s compared to the 1960s, excuse me, there's been an increase, a really significant increase in smoke-related mortality, particularly in Boreal North America and Boreal Asia, as I highlight in the picture. And it's looking at other regions as well, which are color-coded according to the map. But the key point there is this big increase at the boreal latitudes, including the Arctic. And on the right-hand side, there was a study that looked at the transboundary health impact of Arctic wildfire smoke, so this wildfire smoke in the Arctic, but also the subarctic, which is why this chapter focuses to some degree on high latitude fires, seeing this decadal, this from the 2001 to 2010 period to the following decade, this forward shift in the wildfire source of PM 2.5, so having more direct impacts on the health of communities that live in those regions, and particularly closer to these fires, which I'm not showing here, but in those years, 2019, 2020, really persisted for several weeks. In fact, from the beginning of June all the way through to the end of August, those fires were existing, and the smoke accumulating over that period as well. In terms of the environmental impacts, if I just change to the other side of the equation to some degree, there's this excellent web article published on the Arctic Council website, which looks at fire and ice and the impacts of wildfires on permafrost and peatland. So we've heard a couple of times a few mentions of permafrost and the impacts on the cryosphere and on the hydrosphere in the Arctic. And so this is obviously a concern when we're talking about wildfires there. On the bottom left-hand side of this screen, there's a slide I borrowed from Sander Verwerbeek from the Vrije University of Amsterdam, whose group has done a lot of work in advancing our understanding of fuels and fire behavior in the Arctic region. And the key takeaway here was that a lot of these Arctic and boreal fires are geographically coincident with permafrost peatlands. So this is then has an additional concern and additional feedback on the environment and the climate through this change in permafrost and the availability of peatland, which when it burns has a different emissions profile and can have significant impacts on the carbon cycle, as well as the atmospheric composition and air quality. And in the key findings, I mentioned also about holdover fires, and this is related to this slide. And I show here a news cutting from the Edmonton Journal that was published at the beginning of January this year, quoting Mike Flanagan, who's one of the co-authors, where they're looking at the measurements of the catchy term zombie fires, but these are the holdover or overwintering fires that burn underground through the winter and then re-emerge when the snow melts the following spring, and are a significant and growing in importance as an ignition source for fires in the Arctic and the high latitudes. And on the right-hand side, these are very challenging fires to observe, but this is work by Rebecca Sholton, who was in Sander Verwerbeek's group, and this is a work that she did in 2021, looking at using satellite observations, looking at burn scars from previous years to then identify where observed fires the following year may be occurring in those burn scars, which are then providing evidence they may be from overwintering fires themselves. And then this is my final slide. Lightning is also a significant source of fires, and this was a fire in Alaska in June 2022. This burned over a large area with it was the largest tundra fire on record for southwestern Alaska, and so we can see very clearly the burn scar in relation to the active fires and smoke, similar to the images I showed at the beginning. But again, just further evidence that this is changing the landscape. It could change the carbon cycle. We talk in the chapter about the interaction and the non-linear interactions between the cryosphere, permafrost, wildfires, and fire risk, and then the smoke impacts. And so with that, I'll finish my presentation, and thank you for your attention.
Thank you so much, Mark. Due to the time, I think we should just move on to our next speaker. And she will be presenting the chapter on Arctic Ocean acidification. Dr. Agneta Fransson is a senior research scientist and chemical oceanographer at the Norwegian Polar Institute and an adjunct professor at the University Center in Svalbard. The floor is yours.
Thank you. Okay, can you hear me? Yes. Yeah, thank you for the introduction, and thank you for the opportunity to present some key findings from the ocean acidification chapter. So, how do I just push the green? Oh no, that one. Yes. Yeah, so you see, also acknowledge all the co-authors, the contributing to the chapter. You see all the names there at the bottom. And so one a key finding is that the Arctic Ocean is continuing to acidify, we know that, and it's already witnessing environments that are harmful to marine life. And it's also negatively impacting activities, well-being and rights of Arctic indigenous peoples. And the reason for ocean acidification is that CO2 in the atmosphere is increasing steadily, and you see also, you heard also that it's already 427. So you see the red curve there, and the corresponding increase in surface CO2 in the green color, and the pH is decreasing in the surface water, the blue color. And this is from North Pacific in Hawaii, but in the Arctic Ocean, it's really progressing faster, twice as fast than the global oceans. And this is shown for the 20 years, this big change, and is due to the increased ocean CO2 uptake, and that is corresponding to areas where we have the increased sea ice loss and also meltwater. So there are several studies showing this, or a few studies in the Arctic showing the same pattern, and this really huge change. And this is from a study in the north of Svalbard into the deep oceans, and from Ericsson and others, where all have been contributed to this study. And you see from the past in year 2000, in the color in the green circle there is more blue, and how it changed in 20 years until present in 2020 to more orange color. With ocean acidification, we also have got decreased aragonite saturation, and that means that is an indicator we use to show how much or the ocean acidification, the strength on the marine organisms, and how it can dissolve calcium carbonate shells and skeletons. And when it's less than 1, we say it's corrosive for these shells. And or they start to dissolve, or have problems, or they need more energy to cope with this acidified water or low aragonite saturation. On the left hand figure or map, you see there is a large variability, a regional variability in the Arctic Ocean. Or the more red, the lower saturation, and the lowest saturation we find in the coastal areas on the shallow shelves in the Arctic, and the most dark red is below 1. It's corrosive, and it's a Siberian shelf, and this is in the upper 200 meter, and that also corresponding to dissolution of the shell in the same area. If you look on the right hand side on this map, we see a really dark color in dissolution, and that almost 100% of the shell of this zooplankton is called Limacina helicina, and or you can also call it sea butterfly, and it has this thin aragonite shell. So it's sensitive to this low aragonite saturation. And in these areas, it's very affected by the increased fresh water due to river drainage. And we also have the thawing of permafrost and coastal erosion that brings organic carbon that's degraded, and methane, and also CO2 into the ocean. And that causes increased ocean acidification. And that was one of the questions here. I hope I answered this question, what the permafrost actually can do. It increases the ocean acidification. And the ocean acidification affects life of many important species in the Arctic, and it has wide-reaching impacts on the Arctic food web and fisheries. And you see the food web to the right-hand side, where we have all the marine mammals and fish, and lower trophic levels with zooplankton, and also the humans, the Arctic indigenous people or local communities that are dependent on this web, food web. And with also the sea marine mammals important for the Arctic communities as well, for cultural and survival importance. Also important species is a polar cod. And experiments have shown that ocean acidification experiments have shown that eggs and larvae are vulnerable to this treatment of high CO2, low pH. And the largest impact has actually when it's a multistressor and when it's both ocean acidification and warming. So that's the strongest effect, and also found that young species or young juveniles, early life stages of Atlantic cod, northern shrimps, and all kinds of crabs, and also bivalves as scallops, they are also affected negatively to this treatment, warming and ocean acidification. And also the Limacina helicina, the sea butterfly that I shown before, is already severely compromised. Also, Arctic fjord systems are the highly productive areas, and they are currently undergoing transition due to accelerated melting and retreat of glaciers, and fresh water enhances ocean acidification. And in the fjords, there are also a complex interplay of processes. They have the sediments from glaciers, we have permafrost thawing, rivers, and coastal erosions, and methane as well in these fjords. So pH decreased, and also continue to decrease in the models study here with different scenarios, emission scenarios. And they show that emission reductions can drastically slow the pace of which critical thresholds will be crossed. And the model also predict undersaturation with respect to aragonite in year by 2100 for all emissions pathway in the 14 different Arctic regions. So there are gaps in data, and we need more observations and for modeling. So the community-based monitoring led by Arctic indigenous peoples would fill some of these gaps on the regional observational data, and they can be put into models and assist in policy decision making. So the people will help identify environmental changes and drivers and consequences on the coastal and marine environment, and that is important for these people for their livelihood, health, and cultural practice. So one of the lead in the Alaska community, Bobby Schaffer, he said that the changes are happening in a more rapid pace. I feel that the changes will continue to accelerate, and recording these changes with present a pattern we can use to plan for the future. And he also wonder how will these changes affect food security and the ocean acidification affecting our sea mammals, seabirds, and fish. And also, what is the expected level of ocean acidification in the near future, given the human carbon emissions worldwide? So, yeah, to those words, I would just give the summary of the key findings, and you already heard them, so they are just, you can read them, and I just want to thanks for the attention, and yeah, so I can maybe go back to the key findings. How do I go back? Okay.
Thank you.
So, thank you.
I have to say, if there are any questions, please approach you afterwards. Is that okay?
That's
yeah,
okay.
I'm sorry. Yeah, because now we will go over to the last part of this session to go and have a panel discussion. And And to start that, I have the pleasure to have with us today Dr. Jan Fuglestvedt, who is a research director at Cicero, but he's also a vice chair of the Working Group 3 in the Intergovernmental Panel on Climate Change. So I would like to welcome you on the stage. You can have this table up on the stage, please. If you stand here.
Can you hear me? Yeah. So first of all, thank you very much for inviting me to this very important presentation of this very important report. So I really enjoyed watching the presentations, and I think it will be a very important report for the coming IPCC reports.
Yeah, and thank you so much. So what you've heard today, can you say anything about how it relates to how IPCC have said about the Arctic changes previously, and also how these reports are being used in the IPCC, since there is this assessment cycle 7, which is just coming up?
Yeah, first of all, I would say that these results really add valuable information and updates to the IPCC findings from 2021. So our results build on literature that was published until the end of January 2021. So these findings are very much needed as updates. And in addition to being updates, they are also much more detailed and also have different approaches and look at other variables. So I very much welcome this report. So thank you for your great work with this. And let me also say that IPCC in AR6, the previous cycle, had a lot of references to the AMAP reports, both in Working Group 1, but also in Working Group 2 on impacts, vulnerability, and adaptation. So it's an important source of knowledge for us.
Mm-hmm. You did prepare some slides. Do you want to just briefly go through them?
So these are the reports from the previous cycle. We had 3 special reports, one on 1.5, as you may remember, one on the cryosphere and the ocean, and one on climate change and land. And then we had the 3 working group reports on the physical basis, one on adaptation, adaptation, vulnerability, and impacts. That was Working Group 2. And Working Group 3 is on mitigation. How can we reduce the emissions? And then finally, March 2023, we had a synthesis report that brought everything together. And now we are preparing the next cycle and the coming reports. So I will talk about that also.
Yeah.
So then I press the green. So the plans for this cycle is, first of all, to have a special report on cities and climate change, since a very large share of the global population live in cities, and a large share of the emissions come from cities. We will also have a special report on carbon dioxide removal, or methodology report on how to calculate that, and also a report on inventories for short-lived climate forces. And then we have the 3 working group reports, one on the physical basis, one on impacts, adaptation, and vulnerability, and one on mitigation again. And there will be an update on the guidelines on adaptation and the impact assessment, and then finally, again, a synthesis report. So we have just started the planning of these reports, and in December we had a scoping meeting for the 3 working group reports. These will be published online in a few days, and you can have a look and see how your work can fit into these reports. And there are many ways to contribute to that assessment, and I can show that in the next.
I think maybe we can skip that one because I really want to talk to the others as well. So, but maybe Roar and Camilla can come on to stage together. So that would be excellent. I will introduce you while you're walking. So Dr. Roar Skolin is the director of the Norwegian Meteorological Institute, but you're also co-chairing the panel on polar and high mountain observation research and services at the WMO. And I have a question for you first, because all these, our report is based on observations, and at the WMO you are working on this systematic observation monitoring program, and I would like to hear a bit more about what the status of this monitoring is and how it relates to the things we've heard today.
Thank you very much, Maria, for that question and for inviting me. So the World Meteorological Organization is the UN agency responsible for monitoring both the weather, water, and climate. And one of our tasks is to exchange meteorological data globally, so beyond borders, to use the theme of this conference. This global observing network is essential for weather forecasting, obviously, but also for the long-term time series used for climate monitoring. The global exchange has worked well also during crisis and conflicts ever since the Second World War. In the current situation with the Russian war against Ukraine, there is still an exchange of essential data for weather forecasting. However, many of the Russian data that is required for climate monitoring is no longer exchanged. And clearly that reduces significantly the availability of climate data here in the Arctic. More generally, I would say observing the Arctic as well as Antarctica and the high mountain regions is both challenging and expensive. In addition, the use of satellite data is more challenging over ice and snow in general. Therefore, we have less observations in these regions. And that underlies the need for international collaboration to enhance observation network in order to close gaps and also avoid duplication. Avoiding duplication is obviously also essential for reducing our footprint. I would say that here in the Norwegian area, we are lucky. We have the COAT observation program, which has allowed us to enhance the observation in the Varangerhalvøya and on Svalbard extensively. And we also have a good collaboration with the SIOS network on Svalbard. So when you ask how does this report relate to what we're doing in WMO, the fact that the Arctic is changing so fast is something that we use when we discuss with leaders from the rest of the world. The awareness of the Arctic is not very high, I must say. It has, of course, increased over the last couple of weeks due to the Greenland issue. And we could probably expect that it will increase even more. But we need good information to update the world leaders on what's happening in the Arctic and the wider consequences. And here the AMAP report is a great source.
Thank you for that. I would also like to welcome you on the stage, Dr. Camilla Brekke, who is the director of the Norwegian Polar Institute. And you are representing a large research institute with both interest in Arctic and the Antarctic. But I'm wondering, when we hear about the results here today, it seems like it's all going in the wrong directions and everything is changing all the time. So how do a research institute like yours prioritize, and how do you do the research prioritize when everything is such urgent?
Thank you, Maria. Before I answer your question, I just wanted to thank the researchers presenting today. To me, this is really worrying results, and I think that the report needs the attention that we can bring to it. We need to empower the facts, as the State Secretary touched in on. But then, back to your question. Arctic research and polar research is really expensive and risk-taking. And I would like to start with a short answer to your question, a twofold answer. I think that we really have to exploit and use the research infrastructure and research stations that exist. The Norwegian Polar Institute have the leadership and are hosting and also managing the governmental ownership of a number of these. And we do accommodate other national institutions to these infrastructures if there are capacity. And second, I believe that we should pull together and think in large projects so that research institutes and researchers could pull in the same direction. And the 5th International Polar Year is coming up, and I think that's an excellent opportunity to address some of these pressing issues. So if I can say a little bit more and address these pressing issues that we have been talking about today with reference to Dr. Gerland and Dr. Fransen's presentations on the changing cryosphere. We heard that the sea level rise is connected to the melt of the Greenland ice cap, Alaska, and also the Canadian Arctic. So these are serious changes and threats to the environment. And also this change to the cryosphere is a part of the triple crisis this planet is experiencing at the moment. So with the climate change, with the loss in biodiversity and also pollution, especially maybe marine pollution. And a common feature of these crises is that they have evolved over time. So from systems that we used to think of as stable and predictable systems. So now the question is, as we also have heard today, when and where are we facing the thresholds in the Arctic system? And I think that maybe the only way to really, with certainty, to address that is to have consistent and standard collection of data over time. And we also do need to improve our capability when it comes to modeling and predicting to foresee what's happening. Over the last roughly 60 years, we have had monitoring in Ny-Ålesund, the Ny-Ålesund Research Station, and we also have the Fremstrait Marine Observatory. And this helps us to explain and follow what's happening. So we do have infrastructure on Svalbard, but we need also to improve our monitoring in the Arctic Ocean. Yeah, I think maybe I'll stop there.
Yeah, that's many interesting points. And I actually want to talk a little bit more about how to use all these data and make them into policy, because that's also one of AMAP's goal, you know, that these reports will be used as background documents to make climate policies. And ultimately, we want to make Arctic states to reduce their emissions, so we want to make an impact on that. And since I have you here, directors and vice chairs working with science to policy, can you give any experience from your work on how to make those the science into policy and in the most effective way? Do you want to start from an IPCC point of view?
I can start. IPCC is known for writing huge reports, many kilos of report. But on top of the huge chapters, we have a summary for policymakers. And this is written in a language that we hope is applicable and understandable for those who need to use our results. So that is a main interface between IPCC, research, and policymakers.
How about you?
Yeah, I would say that, well, Maria pointed to that it has to be a translation. IPCC is doing part of that, but we need to be even better at translating the scientific results into statements and advice that is relevant for the political discussions that is at hand.
Well, politicians are clever, but they're also very busy. And when we talk about, try to reduce the CO2 in the atmosphere, and to translate that to food security and what you may get on your plate or not get on your plate for dinner, I think that's very important. And maybe to just explain that really, really simple and repeat it. That's what we have to do, I think.
Yeah. Very, very good answers. Due to the time, I think actually we have to close. But thank you so much for those great answers. And for that, so give them a hand. And to end this, I just want to say that the key findings of the report can now be found on amap.no. If you click on the news there, you can find the document with all the key findings. And please approach us if there are any questions. Thank you so much for coming.